Hi, I am Janice, and I will be explaining part 1, Lab E4. For part 1, stepper motor controller, we are required to design a Moore state machine under 3 input. EN input is to enable stepping, while for CW input will control stepping direction, whether clockwise or counterclockwise. The clock input will control the rate of stepping of the motor controller. For this circuit, we are using 4 ICs, which are 107JK flip-flop, 86 2-input exclusive OR gate, 00 2-input NAND gate, and 02 2-input NOR gate. As can be seen here, the state diagram is constructed after the truth table, and the K-map here. So to prove that the stepper motor controller works, so when enable is 1, the output will be anti-clockwise. When CW is 1, it will be clockwise direction. Both of these is in low frequency. If CW is 1 and enable is 0, then the output will remain fixed because the enable is 0, which is fixed. If enable is 1, then the output will be clockwise, and if I increase the frequency, the output appears to be in the anti-clockwise direction because the frequency is 500 Hz, which is too fast to determine whether the output is clockwise or anti-clockwise. So that's basically it.
I would like to talk about part 2. So we are given a schematic, and after we analyze the schematic, we can expect the next state of each present state, and we come up with the state transition diagram. And there are two possibility sequence. The first one is the state will look from 0, 0, 0, and the second sequence is it can be looked from 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and 0, 1, 1, and back to 0, 0, 1. The function of the second NOR gate is to help us to produce a logic 1 to change from 0, 0, 0 to 1, 0, 0, so that we can verify the result. So if the state is initially at 0, 0, 0, we can switch on the ground into 1, then it will move to 1, 0, 0 and continue in the loop. Now we are going to check the result. As you can see, the sequence follow what we expected before, and from the oscilloscope we can observe that the bits generated are not random and it repeated. The reason is this flip-flop, this register only provide 8 bits and it will keep looping after 8 bits. So the sequence will be repeated after 8 bit. That's it. We are going to modify this 3-bit LFSR into a 7-bit LSFR. So generally we remove 2 wires from 4 to 6 and for 5 we move to 12. So this LFSR will help us to produce a pseudo-random bit sequence. So here is the result. We can see that the bit generated is randomly. So you can see the bit generated is not fixed and it appears to be random. The reason is 7-bit LFSR produce 127 sequence and this help will cause it to repeat the sequence after it complete 127 sequence.
I'm Knowledge Chong and I'm going to explain about Lab 4, Part 3. So in Part 3, we designed a millistate machine by using 2D type flip-flop and the LFSR from Part 2 to as pseudo-random bit sequence. So for achieving the output of 0, 1, 1. So at first, we consider the state. First state is idle state. So in idle state, if the input is 1, and it will loop back to itself. If the input is 0, it will go to the next state, which is F0. So at F0, if the input is 0, it will loop back to itself. But when the input is 1, it will go to the next step, which is F01. At F01, if the input is 0, it will go back to the previous stage, which is F0. But when the input is 1, it will achieve the outcome of 0, 1, 1, and the output is 1. And it will go back to the idle state. So from this state diagram, we construct it into truth table. So from this truth table, we find we're using Canomat method to find the input for DA, DB, and the input for output F. And the result is here. This is the input from FSR, and this is the output F. When the input is 0, 1, 1, and the output will be 1. That's it.